Okay, in this lecture, we're going to start out doing an example and talk about how do we get linear interpolation or interpolation functions for a rectangular element. So if you think in terms of applications, what I'm talking about here is taking a single quadrilateral element and pulling this out of some larger scale structure that's over a two-dimensional domain in X and Y. And to illustrate the point, we're going to use local coordinates Y bar and X bar. And this is not just a simple homework or example problem. This is actually what we do when we develop these models. We go from a local coordinate system and construct these functions and then map those back to a global coordinate. It turns out this makes things a lot simpler, being able to evaluate these local elements and then just coming up with a mapping transformation from a bar to a unbarred coordinate system. Alright, so we talked a little bit about what this displacement approximation should be. Remember, we have to be careful in how we define the rank and order of these polynomials such that you can invert and get a unique set of constants C1 through C4. So remember from last time we said we plug in values for X and Y, or in this case X bar, Y bar. So I've put in some values here and we plug those in. You got 4 equations, 4 unknowns. We can solve for C1, C2, C3, and C4 just by manipulation, or you could put this in some matrix inversion software and spit out all 4 terms. So after getting that, then I want to show you what does this look like in terms of our solution. So now what we can do is we can get our displacement solution over anywhere inside that quadrilateral element as a function of the nodal solution. So my U1, U2, U4, and U3, those are the nodal solutions that you solve from the finite element problem. So here we're not completely solving the problem, we're only getting this displacement as a function of position, X bar, Y bar, and the nodal solutions. Talk about how to find these nodal solutions later. But in summary, this is your displacement solution, or some other scalar potential, maybe electric potential, or magnetic potential, chemical potential. This is the functional form. If we get this back into the form often used in Reddy's book, we have these 4 interpolation functions, which basically means you're going through and simplifying these things down, and you can show that they look like this. So this is V1, 2, 3, and 4. So that comes straight out of these relations. So it just gives you a more compact notation. Okay, the other important thing on these problems is determining boundary conditions. So say if you have some domain omega, you've got a boundary I call gamma, and at some points we may want to define this natural boundary condition Q. So these are your fluxes. This may be heat flux, or it could be a force defined in terms of a displacement gradient. So there's some things you have to be careful with when you do this contour integral around gamma to define this flux within a discretized element. So I'm going to talk about that in terms of a triangle. It turns out it's much easier to work again on a local coordinate system. So we have our global XY. I'm going to define a local coordinate that's here. It's parallel to one of the triangle edges, and then orthogonal to that is t. So I have its local st coordinate. So now we have to define some kind of transformation that goes back and forth. So ultimately you have x is a function of xt as well as y, a function of xt. And then you can map these interpolation functions between coordinates. I'm not going through it here. If you reference in the book, here's the equation. This gets back to the fact that these are not your interpolation functions for the nodal solution. This is the weight function. So this is defining geometric relations. So when we do that, we introduce a geometric relation for this so we can relate s and t to x and y. And in the book they go through this. We'll also go into more depth about it. So if I come back up here, here's my side 1 from node 1 to 2. And along here t equals 0, where we connect nodes 1 and 2. So phi I is going to be s and 0. You can write it out in terms of x and y. Turns out here is how we're going to define x and y of s. So what you end up finding is, for a linear interpolation function for a triangular element, a 3-node triangle element, this is what that interpolation looks like. Here is phi 2 or psi 2 and psi 3. So on side 3, between nodes 3 and 1, we get something similar. We get these 3 terms, and it's important to note what I want to do is evaluate. Let's come back up here. So what I want to do is evaluate what is Q1. So this means the flux at node 1, right? So when I take this contour integral, what we have to do is integrate from node 1 to 2, whatever our flux is. Here's our interpolation function. And then we have to evaluate 1 to 3, right? Phi 1 is 0 on side 2 to 3, so this never comes into play in our integral. We only have to integrate 1, 2, and 3, 1. So by plugging in phi 1, we can integrate this out. It's just integrating a polynomial, and then we can get Q1. And this is found along the boundary. So in summary, what we do is we transform xy to this local st coordinate. Second step is, given that, we transform our weight function in terms of the coordinate transformation. Then that simplifies our integration. I've left out some intermediate steps here. If you look at example 8.2.4 in the text, it gives additional examples. If you have more questions on this, let's definitely talk about it in class.